Well, I should begin with saying that quantum mechanics is one of the greatest discoveries of the previous century. It is a marvelous theory that puts everything in context about the atoms, the molecules, and the entire subatomic world. It is all quantum mechanical. But the strange thing about it is, in spite of the fact that it's so successful in describing the world that we know, it nevertheless doesn't describe anything that looks like reality. So we are used to working with complex equations. So the equations were being discovered and they work extremely well. But then you ask, what do these equations mean? And the consensus that people in the previous century reached was that you simply shouldn't ask. You should just calculate and you'll get the right answers, so why worry? You get the answers that are observed in any experiment, so why worry? And the reason is, I think, that reality is very important if you want to have a theory that sounds more likely to be true than another theory. So if the choice is a theory that describes real things as if they are real as they are, or real things as just mixtures of unreal ghost-like objects, then that theory has a much smaller chance of being correct. So I want to know if the theories we have today actually describe reality or not, and if not, can we cure the disease? Can we make a better theory that does describe things as if they are real? I say as if because subatomic particles are so small and there's so many of them that you cannot really describe them the way they are. That's hopeless. But we can try to describe them the way they could be, and the way their description makes totally sense. Like you talk about stars and planets, you also talk about stars and planets that we never have seen, but we know that they are there. So the same thing about particles. We know that there are too many of them to keep them all apart and to say this one is real, this is imaginary. That's not the way it goes. They're all real. But we want to have a credible model that describes their being real. And this is our difficulty today, that models of quantum mechanics today don't even allow us to do that. And now it becomes more serious. We do something wrong.
So my understanding, as I say, is quite limited, but my understanding is that that is the fundamental problem with quantum mechanics, and so for that reason people are turning to other theories for describing reality. But do you believe that quantum mechanics can be corrected in order to describe reality?
Quantum theory is on the one hand so beautiful it shouldn't be corrected, but our interpretation of quantum mechanics should be corrected, because this interpretation is something which I find not very desirable. It's hard to say why it has to be wrong, but it's just not credible to me. I think with Einstein I like to ask the question, is the moon there if nobody looks? And the answer is, of course the moon is there if nobody looks. What are you talking about? And this is the way I would like people also to talk about elementary particles. Of course these particles are there, and of course this beam of particles that we create is a beam of real physical particles, and some of them move this way, some of them move that way. We don't know exactly where all particles go, every single one of them, but we know how they go on the average. Now quantum mechanics only describes that average and never goes beyond that. Whereas I think we should try to go beyond that and say that this is a realistic scenario of what could be happening and how we could be describing reality.
You've written a lot or thought a lot about quantum mechanics, and a lot of people see it as the most accurate, as like giving the most accurate predictions compared to other scientific theories at the moment. But your latest, well, some of your latest work looks at how quantum theory is actually a misnomer. Would you be able to explain this to us?
Right. So there's no doubt, and no one's going to dispute, that there's a mathematical formalism that we know how to derive predictions from, and those predictions can be accurate to 14 decimal places. But what a theory is, what a physical theory is more than just a mathematical formalism with some rules. it should specify a physical ontology, which means tell me what exists in the physical world. Are there particles? Are there fields? Is there space-time? And tell me about those things, and then specify some laws about how they behave, that tell me how they behave through time. And the problem is that there is standard quantum, what's taught as quantum theory isn't a theory in that sense. It's just the formalism. And then what people call interpreting quantum theory, which sounds like a funny thing to do, because you'd say, well, I have a theory, what's an interpretation? What's called interpreting quantum theory is really the development of precise physical theories that make the same predictions or nearly the same predictions that you get out of this standard mathematical recipe. And so this to me clears up a kind of funny question, because often they say, oh, a physicist would say, well, I've got quantum theory, what do I need an interpretation for? Let the philosophers do the interpreting, whatever that is. And that's because the language is misleading them. No, you don't have a theory. You have a predictive recipe. And what we want, as a physicist, what you should want is a theory, is something that makes clear statements about what the world is.
So does that mean that actually quantum mechanics is a lot stronger in its predictions than the kind of public broad audience thinks? Or does it mean that they're not there yet and they still need to work towards having the status of a theory?
Well, there are different approaches that people have been working on. This is a very minority group who work in foundations of physics. So there's a whole approach that goes back actually to 1925 and Louis de Broglie that's called the pilot wave theory. There's another approach that are called objective collapse theories, and Roger Penrose is working on those, and some other physicists, Giancarlo Gerardi particularly worked on versions of objective collapse theories. And these are just different theories, and they all make the same predictions insofar as they have been tested so far. So we can't go into a lab and say which of these approaches is right, even though in principle sometimes these different approaches make slightly different predictions. You have to think very hard about how you could actually test them.
And what does quantum tell us about physical reality?
Well, that's what's interesting, is that these different approaches would give you different answers. So if I say, well, I think it's the pilot wave approach is correct, I'm going to say, well, it tells me that the quantum mechanical wave function is not a complete physical description, and maybe the world is deterministic, and so on. And if I take an objective collapse theory, I'm going to say that tells me the world is fundamentally indeterministic. And so there's no single answer to that. The one thing we know for sure is that there's a kind of non-locality, and this comes from a theorem of John Bell, which doesn't depend on the interpretation. John Bell proved that just certain results that you get in the lab cannot be reproduced in a theory that is local in a certain well-defined sense. So there has to be some non-locality.
Where do you stand amongst these theories?
I mean, I have a slight, but this is just my preference. My aesthetic sense is that the pilot wave approach seems more natural to me, and the objective collapse approach seems to me more unnatural. But I wouldn't, give a lot of attention to my aesthetic preferences here. They're both very serious. They're trying to write the theory down in completely precise mathematical terms. And everybody should pay attention to all the going things that are actually out there that have a chance of being right.
Well, for a long time, we've heard these stories about how quantum mechanics is weird, and how there is this subatomic world or this atomic world that obeys different rules to the ones we're used to, and we have stories that we tell about that, about how particles can be in two places at once, and how they can mysteriously communicate to each other over long distances and so on. And what I'm saying in my new book is that we need to change those stories. We need to change the record, really. And part of the reason for that is that the field hasn't stood still. The questions at the heart of it are the same ones that people like Niels Bohr and Albert Einstein were grappling with when they invented this quantum mechanics. But we know more now. And particularly we know more because some of the experiments that were just thought experiments in their day, we can now actually do with today's technologies and have done. And so we don't necessarily have all the answers about what quantum mechanics means, but we have much better questions. We've refined the questions. And I think this has shown us that these old ideas about particles being in two places at once or taking two paths at once or whatever, they're just our classical attempts, so using analogies from our everyday world to try to develop some language to explain what's going on. So I understand why we have them, but actually they're missing the point. The whole point about quantum mechanics is that it's not classical, that particles don't in any obvious way just take paths through space or just are here or there. Quantum mechanics is counterintuitive in a very profound way, and we need new stories to grapple with that. And one of the ways I think we can start to think about it more productively is in terms of what is knowable and what is not, in terms of information, but in particular in terms of the information that we have access to or that we don't have access to. And one of the productive ways that physicists are now thinking about this is in terms of perhaps there being some imbalance between the number of questions we can ask about a quantum mechanical system, a particle or whatever, and the answers it can give us. That it can't actually, at that quantum level, the world can't give us unambiguous answers to every question we can ask. And when it doesn't, what we seem to get when we sort of run out of answers is just randomness. And the result of that is that things look very strange from our everyday point of view. But we need to sort of shift the thinking away from how it usually works in science, where we think, I'm going to interrogate this system, I'm going to ask a question, and I'll get a result. In quantum mechanics, you don't always do that. So asking, what is this particle like and what is this particle like, you think you should get two answers out of that. But in quantum mechanics, it seems like there are occasions, many occasions in fact, where those two particles aren't actually two particles. They're kind of the same thing, even though they're separated in space. They're you have to think of them as a single entity. And so there's not enough information in that single entity to give you answers to those what seem like independent questions, because they're not independent. They're dependent on each other. I think this, it seems to be what's at the heart of quantum mechanics. So it's really about what questions we can ask and how much information we can expect to get in response to those questions.
So how can we invent a language that suits quantum mechanics better than our current use of language? Have we already made some small steps in that direction?
Well, at the moment, and science has to do this and does it all the time, particularly at the frontiers of physics. At the moment, we invent terms that patch over our ignorance. Dark matter is a term like that, dark energy is a term, and so is, we talk about in quantum mechanics, quantum non-locality, which basically refers to this idea that, to put it one way, the properties of a quantum object aren't all located on that object. Some of them might be kind of related to the properties of some other object. It's as though those properties themselves are smeared out, as though, the goldness of my ring is somehow not just in my ring, it's also in this other object over here. And we say that's quantum non-locality. So there's a word to talk about it, and it's useful to have that word because it stops us then saying, well, but it has to be in this ring. We say, no, it's non-local, so it's not, it's somehow space is messed with here. And sometimes time is messed with in similar ways in quantum mechanics, but it's just a word, and we don't have an intuition for it. And we talk about that also in terms of a property called entanglement. These two objects are entangled together. It's a nice descriptive word, but what does it really mean? So at the moment, we're at that stage. We can invent words that stop us from telling these old stories, or they should stop us from doing that, but they don't really give us an intuition of what's going on. And I'm not at all sure that we'll get past that because of this fact that, of course, our language is the language that you have when you're 6 feet tall and you're living in a classical world. If we were electrons and protons, we would have a language to describe these things, but we're not.